the roundtable discussion session. And yeah, you can ask any question to the three speakers. Yeah, Walter, yeah, please.
Okay, thank you. So I have one question to Enrico, Nora, Dirk. I mean, you have now this non-local collision term, and you were saying that somehow if we use local equilibrium distribution function, then there are problems with this form. Actually, entropy is produced. But I mean that if you have this collision term explicitly, then you can maybe try to figure out some, really local equilibrium, which, doesn't produce entropy. Because somehow my feeling is that you use what we have found before using different approaches. And now I think the kinetic theory should be complete. And if you have the collision term, which is non-local, you can ask the question and look for kind of extended, I don't know how to call it, local equilibrium that really makes the collision term vanishing.
The problem is that,
Do you know what I mean, actually? Because somehow I think that you take somehow the local collision term, which is known from other approaches, but your approach now is self-contained. So one.
Yeah, Wojtek?
Yes, yeah. So I just finished. Yeah, so I think you can just answer this question. That maybe the form suggests some new local kind of equilibrium.
Anyways, it's not that we claim that that is the only one, form that make the collision cannot vanish. This is also our ansatz of the equilibrium distribution form, a function. So,
because usually in the kinetic theory, you have the collision term, and then you look for the distribution which make it.
Yeah.
vanish.
So the thing I would say that here is it's a bit. Yeah. So in the classical case, we know that the equilibrium distribution function makes the collision term vanish and maximizes the entropy, right? The thing is that we don't really have this correspondence here because we don't really know how to write the Wigner function from the the entropy from the Wigner function. So
So you don't have something like H theorem that
somehow we can do what we did in our papers, yes, but since we start from from first principle with the Wigner functions, there is no really definition for the entropy for the Wigner function. So we should somehow postulate some definition for the sort of H function with the Wigner functions. Yeah, this is something that I probably don't have a much better answer.
Sorry, can I interrupt?
Perhaps Dirk wants to make a comment?
Can I make a comment?
Okay, let me just comment.
Okay.
I think the point is that this non-locality that we have found is that operates over the scale of 1 over the Broglie wavelength of a particle. So it's really a quantum mechanical length scale. When we talk about local equilibrium, I think we don't understand this to be the scale on which we consider local equilibrium. We consider a small volume in the fluid, which is still much larger than any microscopic scale. So the next smaller microscopic scale is actually the mean free path, which is still much longer than this small de Broglie wavelength. So we are really thinking about, or we're looking at scales of non-locality that are much smaller than anything on a hydrodynamic length scale. So I believe it will be possible to define a coarse-graining scale that allows you to define something like local equilibrium on scales larger than the coarse-graining scale. But I don't know how to do this. I mean, at this point, I'm just telling you how I believe the solution to this.
Actually, the kinetic theory is the coarse-graining, yeah? Because if you have the kind of scattering in quantum mechanics, you have...
In some sense, yeah. Well, this Wigner function formalism has all scales, no? So you have to devise a clever way to separate the scales again.
Yeah, but if you make the semi-classical expansion, so I think you will make some sort of coarse graining, yeah? Because in the,
No. Sorry,
yeah,
sorry to interrupt, but I mean, the semi-classical H bar over something is still much smaller than the scale you would like to coarse grain over, I think.
yeah, but I mean, for instance, if you have the scattering in quantum mechanics, yeah, and so then you have the plane wave, and then you have, scattered spherical wave, and so you have actually, you calculate the cross section, and you have all, contribution from all, quantum numbers L, yeah. So you have all these partial waves. So actually, you have all impact parameters, but. So then you calculate cross section and you put it into the kinetic theory, then you have no impact parameter because you have just one X position coordinate in the Boltzmann equation in the collision term. So somehow there is a kind of coarse graining where all the information from different impact parameters is put into the one point. So this is this kind of sort of problem. So I think that what you do is somehow you do you try to see details in this coarse graining, so somehow remove it in some way.
Yeah, I'm not so sure we're removing it. I think we are just accounting for some conservation laws inside that scale. But okay, maybe I should stop, and maybe other people would like to say something.
Yeah, perhaps Francesco want to further comment.
Yeah, I wanted to. So since you are talking about local equilibrium, and that with the quantum approach, so defining the entropy as the von Neumann say trace rho log rho, and enforcing say local constraint like the energy density and the momentum density should be given by something which is given, then you may obtain a clear definition of what local equilibrium is. And then you may calculate the all quantities by averaging with this density operator. So in a sense, with this method, you don't have to care about, so I advocate that this method is more general than defining a local equilibrium from a collision kernel. A collision kernel, say, makes physical sense if you have a separation of scales, as Dirk pointed out, between, say, the mean free path and the thermal wavelength of particles. So you have really colliding objects. So objects which are free for most of the time, and then at some point there is an interaction. And this is a kinetic system. But with the method that I have mentioned due to Zubarev and others, then you don't need the system to be weakly interacting, to be kinetic. You can define local equilibrium for a quark-gluon plasma, which is strongly interacting, for instance. And therefore, that this, say, I don't know if this can help to solve the issues that you have mentioned. But I guess that it would be a more general way of proceeding.
Yeah, but more general approaches are usually more difficult to apply in practice, so we can use Zubarev in the non-relativistic version for quantum mechanics.
Oh yeah, you can.
Just as Francesco, and I think you're absolutely correct. But if you are doing a gradient type expansion on Zubarev, if you're doing a gradient type expansion of Zubarev, I don't see how you are going to get anything qualitatively different from Suget's last talk. You'll have a bunch of gradients that are talking to each other, and there will be a constraint on the positivity of the second law of thermodynamics, and it's an effective theory. You see what I mean?
Yeah. Can I answer?
Yeah, sure.
I mean, what I was say contrasting was kinetic versus strongly interacting. So if you have, so the gradient expansion in the Zubarev is the so-called, so requires the hydrodynamic limit. It means that the variation of, so the scale over which the thermodynamic fields vary significantly is much larger than any other microscopic scale. That means, for instance, the temperature and velocity are almost, say, flat over many microscopic distances. But the separation of scale I was talking about is the separation of scale between, say, the thermal wavelength, so it means the mean wavelength of a particle, and the mean free path. So a system is kinetic if the mean free path is much longer than the thermal wavelength. Otherwise, the system is strongly interacting. And if it is strongly interacting, say, the collisional approach may have some problem. So I don't know if this makes it clear. So in other words, there are three scales in the problem. In the problem, you have the mean free path or microscopic interaction scale. You have the thermal wavelength, and you have the size of the system. So if the system,
yes. Yeah, and the appearance of polarization is controlled by the thermal wavelength. You're absolutely correct. We agree.
Yeah. I see a question by Masood in the chat. Masood, do you want to ask by yourself?
Yes, I'm sorry, at the
Please
moment
go ahead.
I couldn't talk. It's basically, it's a very basic and silly question. What is the difference between local equilibrium and having global equilibrium at a certain, for example, fluid parcel? How we distinguish between them?
So this should be a question to the third speaker or the first speaker.
I didn't understand the question. Sorry. What is the difference between global equilibrium and?
No, when we talk about global equilibrium, we are talking about a system that is fully in equilibrium. Yeah.
Yeah. So
like a box. Now, what happens if I take the box as a fluid parcel and assume that this box is not talking to the other boxes, and therefore I use the global equilibrium, and then after that, when I'm going to use hydrodynamics, I localize my results. You know, I mean, it's very, I cannot understand exactly what is the difference between local equilibrium and global equilibrium at one parcel.
Can I say something?
I think I do.
Sure.
Yeah, I think that, yeah, if you assume the global equilibrium in each cell, each fluid cell, you assume that if you calculate the partition function, it is just given by the spatial integral of the some thermodynamic quantity, which is completely fixed by the local temperature, which is, yeah. But if you assume that the local equilibrium, it allows that the partition function to be dependent on the derivative of the parameter. So it is, yeah, somehow more general. So for example, if you consider the chiral vortical effect or anomaly-induced transport phenomena, which is completely fixed by calculating partition functions, and that partition function contains a derivative of the fluid velocity. So if you assume the global equilibrium at each cell, you cannot capture such kind of the derivative corrections. So in that sense, yeah, it is general and different, I think.
Yeah, okay. Wojtek, do you have a further comment?
No, but it's a good question actually, because I think I started thinking, but cannot say anything precisely. I started thinking about thermal vorticity, because thermal vorticity should be constant in global equilibrium, I think as a tensor. So now if you go to local, it should somehow depend on space-time coordinates, right? We have to make it free somehow. But then should we have an equation for this as the independent quantity? Then we somehow come to the idea maybe of this spin polarization tensor, which is independent of thermal vorticity. Yeah, you asked me about, I started thinking and I said what I had in mind, but I think it's a good question actually, because this is what we do usually, that we have, big system and we divide it into smaller parts and we say that each of those small fragments is like a thermodynamic big system, and we can be treated as being in global equilibrium. Yeah. So it's a good point, but now we have another, thermodynamic quantity, which is actually gradient. And this is kind of qualitatively different situation. This is not only a function like the temperature or pressure, but we have thermal vorticity, which is the gradient. Rotation, rate of rotation, and we now want to make it also local.
Wojtek.
Yeah, go ahead, Francesco.
Yeah. I cannot say anything more.
Global equilibrium is when entropy gets maximum. So it cannot decrease anymore. Okay.
The of the total system, yeah,
the total system. Yeah, global equilibrium is when entropy achieves the maximum. It cannot decrease anymore. Okay. Like for instance, if you have a system if you have as an isolated system with angular momentum, entropy can increase up to some point and then it has to stop. And this happen, and the configuration is such that it is rigidly rotating. So this is what Landau proved in the statistical physics book. So when entropy is maximal, then it's global. When entropy is not maximal, and still you are in a situation where the temperature, you can define a temperature locally, means that you have systems which are approximately, say, if you divide into boxes, each box is approximately the thermal system, then it is local equilibrium. But entropy is not maximal yet. I don't know if this is a good answer.
Yeah, but on the other hand, it's if you have adiabatic change, like in perfect fluid, I think it's conserved. Yeah, of course, it's an approximation.
I have a comment about this. The problem is that entropy certainly in a quantum field, entropy's entanglement entropy and things like this are frame dependent. So in a system which is certainly in a non-inertial frame, like a rotating system or something like this, one has to be a little bit careful when you talk about entropy is maximized, but entropy is maximized in what frame? The second law of thermodynamics is defined usually locally. You have an entropy creation and you have an entropy current violation. And this might generate some confusion. I mean, the way in a kinetic system, the way the speakers of this session defined it, is not guaranteed to reach global equilibrium the way Francesco defines it. And this is why, a couple of days ago, we were discussing about the KMS condition. This has something to do with this. If you have a global equilibrium which doesn't obey the KMS condition, it might be something that local equilibrium will not reach. Certainly assuming things like one particle Wigner functions and cutting off two particle Wigner functions. This approximation is also related to the hierarchy that Francesco mentioned of the thermal wavelength versus collisions.
Yeah. Okay, Jinfeng, do you want to Add a comment or do you have a question?
Yeah, this is the trying to follow up the discussions from Dirk and Francisco on the excuse me, on the scale of the hydro. So so my question is the following. So suppose that we have a macroscopic fluid scale that's much bigger than the mean free path scale, which is say bigger than the spin orbital coupling quantum scale. Shouldn't one then conclude that the spin somehow is always locally equilibrated with the fluid cell? The fluid cell's angular momentum, what I mean is. In other words, I'm trying to say that doesn't that imply that the spin tensor in itself is not independent? It has to somehow always be equilibrated locally. If I take your argument about the scale.
Yeah, maybe
Yeah, but
Dirk. Yeah, Walter. Yeah, please go ahead. Yes.
Thermal vorticity, you know, so the gradient is actually between different fluid cells. Yeah, because this.
I understand. Let's say, suppose I take a fluid cell scale that's much bigger than mean free path. Of course, it's still much smaller than the macroscopic scale.
Actually, Masood, if I can come back to Masood's question, which is very good actually, because you know we divide a big system into smaller systems, and we treat small systems as being in global equilibrium. You know, in this physics without spin. And now somehow, if we have thermal vorticity, actually we have the quantity which connects the different fluid cells, because the gradient in thermal vorticity is actually gradient between different fluid cells. Yeah, because we somehow take temperature at different points and calculate the the ratios. So somehow it's
no, that's correct.
Completely different than the standard, I would say, idea of dividing big system into small systems.
No, but that I thought is a different situation. What you said, I understand, but in that case, of course, you're talking about like thermal vorticity. But here, which of course supposedly should be the case for the global equilibrium, right? If we just look at one single cell that is big enough, it can have a angular momentum chemical potential omega mu nil, which doesn't have to be the thermal vorticity, but the spin has to follow that angular momentum of the cell. That's what I try to
Yeah, but if we want to somehow use the results from a large big system in global equilibrium, then we come to thermal vorticity. Yeah. And now if we want to divide the big system into smaller systems somehow, and we want to use the same idea, I think there is the problem, because thermal vorticity connects all these smaller fluid elements. And
no, I understand. No, but that's exactly what I'm trying to maybe understand. So either that one could have an independent spin, or like quote unquote spin chemical potential omega mu nil, which doesn't have to be thermal vorticity.
I think this is what Enrico showed.
That's right. That's what the point I'm leading to. So you don't have to care about for the cells around.
So this picture in mind we had 3 years ago in Darmstadt with Enrico and Freeman, that I think it's quantity is sort of independent.
Yeah.
And I would dare to say that this is supported by the data, unless there is kind of a huge error in data analysis in some theoretical papers, but all the theoretical papers I think are consistent. So
it depends.
So there's some hint. Yeah, you mean?
Depend on.
This was shown by Enrico. I think the picture where you have these two cylinders. So if the time scale which is needed to say, so in other words, if the spin orbit coupling, if you wish, is very small, then you may have a situation where a relativistic fluid has particles which relaxes so slowly the spin of particle relaxes so slowly to equilibrium, then effectively you have to introduce this spin potential in order to describe the polarization of this fluid. If the spin orbit coupling, on the other hand, is large, which means that the relaxation time is microscopic, is very, very small, then the local polarization is always locked to the thermal vorticity, as Enrico pointed out. So I don't know if this was a question, but
yeah, no, that's certainly a relevant point. So in other words, remember, thermal vorticity could become a derivative term. So there's a scale for that. I guess maybe what I'm sort of lingering around is that in a situation, let's say, so should one choose the fluid cell side to be, let's say, suppose we are able to choose the fluid cell side that is smaller than the variation of temperature field. Then in this case, we don't have a thermal vorticity, or thermal vorticity is literally zero within my cell, but I still have an angular momentum. Is that possible?
no, I don't think at global equilibrium. I don't think so.
No, not global. I'm trying to sort of figure out if one do have some hydrodynamic kind of picture for angular momentum, then what would be the proper scale for the fluid cell, or is it not possible at all?
Well, I think that in the transient dynamics, you may have the finite spin angular momentum in your given fluid cell, but after some time, it will relax, so it will be almost disappear. So I think it is similar to the electric field and the chemical potential gradient. So if you apply the electric field, the current flow, and eventually we have the chemical potential gradient, which cancels out the electric field. And the similar dynamics occur for the spin angular momentum density. So if you have finite spin angular momentum density, it will create, or it will relax the thermal velocity value. So at the transient, only at the transient dynamics you can find that finite value. I see.
So in some of this hydro work, for example, from WATEC and the collaborators, you guys assume a spin chemical potential omega mu nu that is not necessarily the thermal vorticity, right?
Right.
So isn't that assuming that at least within your fluid cell it has a time window of independent evolving rather than following the thermal vorticity?
Yeah.
Yes, so actually, this was this picture, which was, I think, realized by Enrico, I think, and Formalism and collaborators. That, there is a mechanism that eventually, the spin chemical potential time to thermal vorticity, because there is this coupling discovered in non-local interaction.
Mm-hmm.
I have this picture in mind that start with spin chemical potential, I think 6 degrees of freedom that are needed to fulfill 6 equations for angular momentum conservation with spin. But if we have non-local interaction, then eventually we have to go to, to thermal vorticity, although maybe the time during the collision is not sufficient that this happens. And maybe the data support this.
So for this to work, should I take it that the spin orbital coupling should be like quicker than the fluid evolution?
Yeah, but the polarization is measured at lower energies, where we have, in fact, not quark-gluon plasma, but we have gas, lambda.
No. I'm asking purely theoretical question. That's the phenomenon.
But then we have the interaction, mediated by mainly pions, I guess. And I think this interaction is dominated by the S wave scattering. So maybe it's really, you know, the physical fact that there is, you know, no spin orbit interaction.
Mm-hmm. Yeah, and I mean, I understand. Of course,
I'm not sure what I said, but if we have scattering dominated by pions in S wave, probably there's no spin orbit interaction at all, where the effect is seen, you know, of the polarization.
Mm-hmm.
We talk about quark-gluon plasma, but this is a long way to accomplish, you know, the formalism for quark-gluon plasma, because we have new problems with gauging variance and other things. But if we think about effective hadronic models for low energies, okay, I guess it's a good thing that we can forget about gauging variance issue.
Yeah, okay, I think maybe we can continue
yeah.
to let some other question pop up. So Nora, do you have any question?
Yes, I wanted to ask something about what Francesco said, that you can define the local equilibrium, because I'm not sure if this is a contradiction to what we say, because does it mean that the collision term, that the non-local collision term has to vanish for the entropy, for the local equilibrium we define from the entropy? Because I think in the Boltzmann equation, the local equilibrium was not the solution of the Boltzmann equation before, because on the left-hand side, there's some gradient. And then the only difference is that now on both sides of the equation, we have gradient terms, which do not vanish if you only look locally. So if you only locally, things are in equilibrium.
Oleg.
Well, I also have a question to Enrico and Francesco concerning local possible pseudo-gauge non-invariance in local equilibrium. And just I have a question concerning the gravitational aspects of energy momentum tensor. As energy momentum tensor, as it was repeatedly mentioned, is a couples to gravity. This allows to derive equivalence principle as a low energy theorem starting from conservation laws. And just I wonder, shouldn't the possible dependence on pseudo-gauge transformation lead to violation of equivalence principle, which would be highly undesirable, I would say. And what Masoud mentioned, the transition to small system from local to global, I would suspect, because so maybe just the extra constraints, just I would say maybe for boundary for terms between these two, between this small system, which will still keep the equivalence principle valid. So this is my question. Gravitational aspects of that.
I don't know if I know the answer to your question.
I have the answer, which is a root one. You know, it has nothing. Our field has nothing to do with GR, with general order of relativity. Of course, maybe one can use the formalism from GR, but GR is a classical theory, and our antisymmetric part of the energy momentum tensor contains H bar. So I think there is, you know, it's a completely different story. GR is classical, non-quantum effective.
No.
Yes, yes.
No. The point is that there is equivalence principle on the action of the spin. Well, it's known, and this tells that spin. Of course, gravity is classical, but spin is quantum, and well, this is, I would say, it's quite well known for years. And just there is equivalence principle, and this leads to the motion of quantum spin exactly as classical rotator. So this is just the property. So it's much less known, of course, but it exists. And just also, I would expect that it should be valid also just in local equilibrium. And so maybe just, again, I don't know the full answer, but maybe there are some extra constraints leading to the still validity of that.
You mean what applies, what you say applies also to the Einstein-Cartan theory? Is what you
Yeah, but actually it's already in just normal gravity, Einstein gravity.
Yeah, but
and
in that
the
case,
action of gravity to spin, so-called gravitational form factors in particular, and the result of equivalence principle is that precession of spinning in gravitational field is exactly the precession of classical angular momentum, and it's naturally the equivalence principle. And so it follows from the conservation laws of energy momentum and angular momentum. Again, if the question is it safe also in local equilibrium? I would.
These are mathematical speculation. You know, this has nothing to do with reality, I would say.
No, it is well. This is even tested by the in experiment. It was there are experiments how.
So you don't have precession of spin in gravitational.
Oh yes, sure. This is so-called probe B. No, there is also this is quite known. Yes.
But this is not quantum effect we are discussing.
No. Spin is of course spin is quantum, and the whole equivalence principle here, it tells that action of gravity on quantum spin is exactly the same as action of gravity to classical orbital momentum. So this is well, this is no. The first paper was, I don't know, by Kobzarev and Okun. Then it was paper by Hans Pagels in '60s on gravitational form factors. So this is quite just developed field.
Okay, maybe I had something different in mind. I had in mind that somehow this antisymmetric part of energy momentum tensor in our field contains always h bar, so we cannot put it into Einstein equations.
No, but no, the point is, of course, there is no. It's not an Einstein equation. It's action of classical gravity onto quantum spin. It's contained in h bar. You are absolutely right. And somehow people undermine this. I would say that something is already known about gravity action to quantum. Exactly, it's action of gravity to spin.
It is semi-classical gravity. So the right-hand side, Einstein
Yeah,
tensor
gravity
is
no, gravity remains classical. Gravity is classical, but we can consider motion of.
Matter part is treated as.
But spin
matter
is
part
quantum,
contains
yes.
h bar.
Yeah. H bar is in spin, of course, but we can also consider action of classical, I don't know, magnetic field to quantum spin, and no problem here. So
also classical spin, probably, like.
No, but we, of course, everything. But action form factors, like form factors accumulate the action of classical electromagnetic field to quantum spin, also gravitational form factors, which are matrix elements of energy momentum tensor, they accumulate information about action of classical gravity onto quantum spin. And it's possible to derive this, how to say, post-Newtonian, I call it post-Newtonian approximation to equivalence principle, that really the precession of quantum spin in gravitational field is the same as precession of classical orbital momentum.
Unfortunately,
it should be universal.
Thanks.
Yeah.
But how does it rule out the possibility of asymmetric T mu nu?
It's not ruled out, but somehow it's. But you cannot use the argument from GR to argue that all energy momentum tensors should be symmetric.
No,
But in the Einstein-Cartan theory, you can define Trollmeder's theorem.
Yeah, but it's an extension. Yeah.
It's extension. Yes, it's not conventional general relativity. Yes.
In general, sorry, can I say something?
Yeah, sure.
In general relativity by Einstein is based on a symmetric T mu nu. And
symmetric.
Symmetric, yes, symmetric. So, and in the quantum field theory books, so at least in Weinberg's, you can read that the Belinfante so in a semi-classical gravitational theory, the mean value of Belinfante is identified with the T mu nu which is needed in general relativity. If one could show a physical effect of the existence of a spin tensor, then gravity should be modified. Okay, and the easiest extension of general relativity that we know is Einstein-Cartan theory, where the torsion is algebraically related to the spin tensor. The point is, do we see some physical effect of the spin tensor?
This is also,
I don't know. The answer is I don't know.
Yeah.
this was also
somehow
a question, because normally one is starting from tensor just arbitrary canonical tensor containing antisymmetric parts by doing pseudo-gauge transformation. It's possible to show that, okay, still the action of gravity is the same, like remains. You can use conservation law with canonical energy momentum tensor, and it defines the matrix element of symmetric tensor. Then conservation laws provide the equivalence principle. And I would suspect this might be universal. That was my question about local equilibrium. So again, might be there are some extra constraints for, or maybe automatic, I don't know, for local equilibrium, which still would allow this. And maybe this idea just mentioned by Masoud and Wojtek, that it's possible to go to small system and to global equilibrium, it's partially an answer. So just, or maybe completely the answer. So you can go to a small system, then there is no dependence of pseudo-gauge transformation, and then equivalence principle is safe.
But guys,
usually if you would like to consider if you would like to consider the coupling to the gravity, it is not so good idea to use a canonical energy momentum tensor.
Exactly.
Usually we use gauge current. So you should define the energy momentum tensor as a variation of the action with respect to the Fierbein or the metric.
Absolutely. But conservation and conservation laws produce canonical. And using conservation laws, it's possible to fix action to gravity. And it includes the pseudo-gauge transformation, but say for in perturbation theory, for electrons in gravitational field or hadrons, this is actually, last week I just posted the reference to my paper on that. So it's possible to perform pseudo-gauge transformation and use the conservation laws to constrain the matrix element of symmetric energy momentum tensor and therefore the gravity coupling. In some sense, the coupling to symmetric tensor is may be considered as a microscopic form of equivalence principle. Using the conservation laws, it's going to macroscopic, so that all the experiments really lead to the falling the same.
I think,
But in quantum theory, T mu nu is a local object which is not measured. It's not physical. This
it's matrix. Like sure. It's matrix element of all this. It's measured by.
You make some averaging over.
Exactly. Matrix element. What enters is matrix element of it, and matrix element just is. The properties of matrix element provide the just possibility to perform pseudo-gauge transformations.
My understanding is like this, that somehow energy density, which is in the quantum T mu nu, has no really physical meaning, it's not measurable. And then
in some sense, matrix element of energy momentum tensor are measurable, right?
I agree with Wojtek, sorry.
And then if you make coarse graining somehow, if you go to classical thing like you want to use in GR, you actually make these systems larger and larger. And at some scale, you have kind of system which can be treated as the isolated system because the energy of the interaction is proportional to the surface, not to the volume. And then this object is, independent of pseudo-gauge transformation because you can use these general arguments about the isolated system, that it doesn't matter what you do. I think the total T mu nu is the same. And this T mu nu enters GR.
Well, actually, situation here is similar to current. So for current, is the coupling of current to electromagnetic field is the same as coupling of energy momentum tensor to gravity. So indeed, you take matrix element and there are form factors. And indeed, if it is possible to consider the small system, well, if there is no the possibility to make pseudo-gauge transformation, again, there is relation of conservation laws to equivalence principle.
I think just the general relativity, the gravity does not see the anti-symmetric part of T mu nu.
Absolutely, but in conservation law, it is, right?
Right, but this does not rule out the possibility of the anti-symmetric part in the energy momentum tensor.
You know, in the book about quantum field theory in the lectures of Coleman, he says actually you can invent 52 actually energy momentum tensors, all are good, including you know, mine, I mean Coleman's last option, you know, so they have no physical really.
But in general relativity, T mu nu in principle can be measured because
right, but it's classical.
Yeah, no, because because it is a local theory. So if you measure the local Riemann tensor, that in principle can be done in the general relativity, then you know what the T mu nu is. Okay. The point is that quantum field theory is not a local theory. So the measurable quantities are momenta, and they are not local. Particles are not local, and therefore they are completely, you know, at variance with each other. And from this say discrepancy or from this clash, then all problems arise. But that is why it is difficult to reconcile the classical theory like general relativity with quantum mechanics.
Yeah, but this is indeed done. So by just the object which I just mentioned, the gravitational form factors and.
Oh, sorry, I have to leave. Okay, bye.
Okay, bye.
Me too, I guess. So. See you tomorrow.
Yeah, it's already quite late, I think. Maybe we can. I think we can continue the discussion if you want, but maybe we formally stop the roundtable discussion session. But if you want, we can continue the discussion. So I'm gonna stop the recording.